in the first session after the conference dinner. So first up we have Kristina Giesel, who will tell us about relational dynamics and quantum gravity. Thank you.
Yeah, thank you very much for the introduction, and also I would like to thank the organizers for this wonderful workshop and the opportunity to speak here. So I would like to talk about the role of dynamical reference frames in the context of formulating quantum gravity models, and my background is loop quantum gravity. So in this talk I would like to discuss a specific approach to formulate models in quantum gravity, which basically follows these three kind of steps. So the way we formulate quantum gravity models in this talk is that we take a classical theory as a starting point. So this will be general relativity. Then I use a specific method to go from the classical to the quantum theory. I will use canonical quantization to obtain then the corresponding quantum model. And I will formulate the classical as well as the quantum theory in a relational way. And this is implemented by dynamically coupling an observer already at the classical level. And I would like to discuss in this talk that in each of these steps, the role of the dynamical observer is relevant and also influences how I perform these individual steps. And before we move to general relativity, let's take a warm-up example, relational quantum mechanics. So first consider canonical quantization in non-relativistic usual quantum mechanics. We know how to do that now since 100 years. And if we canonical quantize, the classical starting point is a classical model in Hamiltonian language. So the kinematics is usually defined in terms of a phase space, which is coordinated by position qj and momenta pj. They satisfy a standard Poisson algebra shown here on the right. And the dynamics in these models is encoded in a Hamiltonian function, a function on phase space. And giving the Hamiltonian, I can determine the evolution of the classical configuration variable q and the momenta pj. Now, when we quantize such a non-relativistic classical mechanical model, we are looking for representations of this Poisson algebra, of an abstract operator algebra on some Hilbert space. In these simple models, the Hilbert space is just L2R. We have the Heisenberg algebra for the corresponding position and momentum operators, and we quantize the dynamics in a function-preserving way, meaning that we take the classical Hamiltonian function and evaluate it at the corresponding position and momentum operators. Then we have two ways of describing the quantum dynamics, either using a Schrödinger equation or using the Heisenberg equations, which are the quantum version of the classical evolution equations. And here, if the role of time is considered, it's just a dynamical, an external non-dynamical parameter. So how do we formulate that in a relational manner? So the most simple version to do that, is to extend the classical phase space by 2 additional degrees of freedom. Let me call them capital T and the momentum pt, which play the role of time. So they become part of the phase space. They also satisfy a standard Poisson bracket. And then this system can be formulated as a constraint system with one constraint C, which relates the momentum of the clock and the original Hamiltonian in the unconstrained system. Now what we would like to do is we want to define on phase space quantities related to, should be a smaller q here, to q and p, such that these quantities commute with a constraint, Poisson commute. And in general, this will be functions of the original q's and p's, the time on phase space. And by requiring this condition, I can construct these functions. And then the relevant algebra for the quantization is no longer the kinematical one up here, but the one of these, what we call observables. Observables because they commute with a constraint in the system. Here in this simple model, it's also a standard Poisson algebra, so simple to quantize. And then we can go in a perspective approach in which we formulate the dynamics of these observables with respect to the time which I included in phase space here. So let me call the time parameter this time in phase space can take tau. Then we can write down evolution equations in this tau parameter for these observables also in terms of a Hamiltonian set of equations with something which I call physical Hamiltonian. And in this simple model, it's just the original Hamiltonian we had before, H, evaluated at these observables. And this would be the classical starting point for quantizing the system, and which means the relevant algebra is now this observable algebra. Since it's as simple as the kinematical one, I can use the same representation, the same Hilbert space. I get a corresponding Heisenberg algebra for these observables, and I can write down the two dynamical equations, either the Schrödinger equation or the Heisenberg equation, which now include these physical Hamiltonian. And this is the idea that we would also like to carry over to general relativity. So if we do that and want to quantize gravity, what are the differences and challenges that we face if we would like to carry over this kind of technique to general relativity? So first of all, it's a more complicated classical theory. It's a field theory. It's the classical starting point is the Einstein's equations, shown here on the right. So here we have the Einstein tensor in terms of the Ricci tensor, the metric, and the Ricci scalar on the left-hand side, describing the geometry of space-time. And on the right-hand side, we have the energy momentum tensor of any matter that we would like to couple to GR in our model, which is just encoded in these phi j degrees of freedom here. There are many other approaches to quantize the Einstein equations. Here, as I mentioned, I will focus on a canonical quantization in the framework of loop quantum gravity. So now, if we think about the classical starting point, in this simple example, I had one very simple constraint. If we go to GR, the form of the constraints is more complicated. The constraints in GR represent the diffeomorphism invariance we have. It can be understood as a gauge symmetry in this context. And it's also a fully constrained system, which means that a priori there is not a natural choice of a Hamiltonian in GR. Yeah, so when we think about this physical Hamiltonian I was mentioning before, then we can introduce this, but only once we choose a reference frame. And this brings me to the second point, because we would like to construct gauge invariant quantities, things which commute with the constraints of GR to respect the diffeomorphism invariance. And we can do that in a specific or in a systematic manner after we introduce some kind of reference frame. If you ask what is the general algebra of all Dirac observables of general relativity, it's a very challenging task to construct that. Therefore, we simplify this challenge by taking a perspectival approach where we choose a frame, and then with respect to that frame, we can construct these gauge invariant quantities. Furthermore, if we want to quantize both sides of the Einstein equations, we do not only quantize matter, but also the metric, which means we need a quantum theory in which we can formulate operators corresponding to the metric and the curvature. And this, in a sense, will influence the choice of representation we choose. So the standard Fock representation we know from the standard model will not work in this context. And in this talk, I want to address these 3 points for closed and open quantum field theoretical systems. So let's start with a closed system and see how we can define relational dynamics in the context of loop quantum gravity. So loop quantum gravity starts with the classical Einstein equations, but formulated in a specific choice of variables, which are the so-called Ashtekar-Barbero variables, which are a connection variable as the configuration variable A. J is an SU2 index, A is a spatial one-form index, and the canonical conjugate variable is the densitized triad. Capital A is again the spatial index, J an SU2 index, and they can be shown to satisfy a standard Poisson algebra. Yeah, so simple Poisson brackets in field theory. Now, using this starting point as the variables, we perform like in the ADM case, a 3+1 split of space-time. So we slice the 4-dimensional space-time into 3-dimensional hypersurfaces. And we can do this if we restrict to globally hyperbolic spacetimes. Then we get a set of constraints. C is the Hamiltonian constraint, which is generating transformation from one hypersurface to the other. CA is the spatial diffeomorphism constraint, generating transformations within these hypersurfaces. And since we work with these connection variables, we get an additional SU2 gauge constraint GJ here. Then we can use the canonical Hamiltonian of GR, which just consists of a combination of the constraints that are involved in the theory. So this will vanish in the physical sector because all constraints are required to vanish. And then we can write down the Hamiltonian evolution equations here in the dynamics. And these equations, together with the constraints, are equivalent to the Einstein equations in the Lagrangian formulation. Now we use this as a starting point. It's a field theory, so we smear our classical quantities. The smearing that we use in loop quantum gravity is a specific one to respect background independence, meaning we want to define these quantities without reference to any metric, any background metric, and therefore instead of using the connection, we use the path-ordered exponential along one-dimensional curves in the spatial manifold, which is the holonomy. And the conjugate variable is then the densitized triad integrated against two surfaces, which we call the flux. And giving this algebra, we can determine the algebra of the smeared quantities, which is the holonomy flux algebra, and that would be the kinematical starting point for loop quantum gravity. Now, how do we implement gauge invariance? We want to use the relational formalism. So the metric at a given space-time point is not a gauge invariant quantity because it changes under diffeomorphisms. However, if I determine the metric or the value of the metric with respect to the value of another field, I can construct combinations which are gauge invariant. And this is the idea. So suppose we have here a spatial hypersurface with point x and labeled by some coordinate t. Then the metric evaluated at x and t would not be gauge invariant. But if I have, for instance, a free-falling observer or a family of free-falling observers, and I consider the proper time along these geodesics, and instead of x, basically the intersection point of this geodesic at the point x in the spatial manifold, I can build physical temporal clocks and rulers in order to define a gauge invariant version of the metric. And how do we do that in practice? Like in the quantum mechanical example, we extend our phase space by additional degrees of freedom. Let me call them Ti and Pti. If I want to reduce with respect to diffeomorphisms, I would need 4 of these additional fields. 1 for the Hamiltonian, 3 for the spatial diffeomorphism. And these fields should satisfy the condition that they are at least weakly canonical conjugate to the constraints. So weakly means on the constraint hypersurface. So I'm allowed to have constraints here on the right-hand side that vanish in this sector. Then we choose the values these reference fields can take. Let me call them tau I. And then for a given phase-space function, as for instance the metric, I can construct its gauge invariant extension by considering powers of the reference field minus their values, weighted by Poisson brackets of, let's say, f being the metric and the constraint. And this combination here can be shown to commute with the constraints, Ci, such that these are satisfying the condition of being gauge invariant at the classical level. Now I choose one of these reference fields to be the temporal one. Just without loss of generality, let me call T0 to be the temporal one. Then we can describe the dynamics as in the quantum mechanical example with respect to the values the temporal reference field take, T0. And we can write it again as an Hamiltonian equation with respect to a physical Hamiltonian. The form of this physical Hamiltonian will depend on the reference frame I choose here on the top. What do we do here? If we formulate GR in this relational manner, we have mapped it into an unconstrained system. So if I resolve with respect to all constraints, I basically have the gauge invariant content of the theory, and then I'm looking at its dynamics. And since these are gauge invariant quantities, I can basically apply any gauge fixing, and then the equations are still valid. Now in practice, we often take a subset of the constraints, reduce them classically, and reduce some of the constraints in the quantum theory. So for loop quantum gravity, the Gauss constraint I was mentioning at the beginning is usually solved in the quantum theory, and the Hamiltonian and diffeomorphism constraint in this approach are solved in this way at the classical level. So now, which reference frame to choose? So far, this was some abstract additional degrees of freedom in the phase space. So the main aim, if I talk about quantum gravity, is to complete the quantization program. So why may I run into this situation that I'm not able to complete the program? I will discuss in a minute. But in order to have such a situation, we are often choosing reference frames which allow a so-called Kukash decomposition. And by this I mean at the kinematical level, where I have all my phase-space degrees of freedom, and I have a very simple kinematical algebra in terms of Poisson brackets. Once I choose a frame, I was mentioning we are interested in the algebra of the observables corresponding to these quantities, and we have to compute the Poisson bracket of these more complicated phase-space function. So in general, this will be more complicated than the kinematical algebra, and we also know, once we choose the reference frame, what occurs here on the right-hand side. So what enters here is the observable of the corresponding Dirac bracket. So the Dirac bracket enters, it's a modification of the Poisson bracket that takes the constraint structure into account. We have second-class constraints here, that's why this Dirac bracket occurs. And depending on the choice, the form of the Dirac bracket changes depending on the choice of the reference frame. And therefore, if you choose a clever reference frame, this right-hand side might be simple. If you choose a more inconvenient one, it might be more complicated. At the classical level, this doesn't matter. But here, I would like to quantize this algebra. Yeah, so I can make my life very complicated if this algebra is complicated, or very simple if it's, for instance, as simple as the kinematical algebra. And therefore, this Kukash composition is a situation in which this algebra satisfies also standard Poisson brackets, and then the quantization is as simple as possible. Similarly, if I think about quantum reference frames and how this relates to the choice of the algebra here, then one can understand the corresponding quantum dressing, yeah, which corresponds to the quantum version of constructing these observables, as a similar algebra deformation, which in the classical limit reproduces this Dirac bracket structure that I'm showing here. Now, the advantages of choosing reference frames which give me a simple algebra on the right-hand side here is that we can complete the program. And if this algebra is too complicated, you can run into the situation that you don't find representations and you have to stop the quantization at this point, which means we cannot complete the program, which means we cannot formulate our quantum gravity model. Therefore, if we think about choosing the reference frame at the classical level, it means the choice strongly influences how simple it will be to find the corresponding quantum theory. Now, what kind of models satisfy this kind of Kukash decomposition? What people considered in the context of loop quantum gravity is, for instance, coupling dust fields. This is the Brown-Kukash dust, which was originally introduced for general relativity and then used in a Wheeler-DeWitt quantization, where you couple additional scalar fields to general relativity dynamically. At the first place, these are 8 additional fields. This is a second-class system, so then you reduce the second-class constraints and you end up with 4 additional degrees of freedom that you can use as a frame. Similarly, people looked at 4 scalar fields or just 1 dust field to reduce with respect to the Hamiltonian constraint only. And all of them satisfy the condition that the algebra I was talking about of the observables on the slide before is simple so that we can perform the quantization. And in this sense, we can then formulate an observer-dependent or frame-dependent model for full-loop quantum gravity, where we then quantize the Einstein equations in this manner. How does this look like? So we consider the observables of algebra for the holonomy and fluxes. We can compute it. Since we chose a clever reference frame, it's a simple algebra. We can use the Arsteker-Lewandowski representation that we use in LQG. It's also an L2 space over the set of generalized connections with respect to the Arsteker-Lewandowski measure. And then we can construct corresponding operators for the holonomy and the fluxes. Holonomy become generalized multiplication operators, fluxes derivation operators. And then we get a physical Hilbert space, which can be constructed as a direct sum of so-called graph Hilbert spaces, H gamma. And in these graph Hilbert spaces, I can construct a so-called spin network basis. And a spin network lives on a specific graph gamma, which is just a collection of these one-dimensional edges that meet in vertices. So these graphs have finitely many edges, and we color those edges by spin quantum numbers. Yeah, and then one can show that if I change the coloring, this would correspond to different basis state in such an H gamma Hilbert space. Now the dynamics, this physical Hamiltonian can be also quantized on these graph-wise Hilbert spaces. And the details are not so important, but I just want to emphasize this is the physical Hamiltonian for the Brown-Kukash model. It's a square root Hamiltonian, and what basically enters here is C dagger C, which is the geometric or the quantization of the geometric contribution of the Hamiltonian constraint. And here we have some geometric contribution of the spatial diffeomorphism constraint. Yeah, and then we quantize this on the spin network states. So we use techniques from lattice gauge theory to formulate these Hamiltonians. And once we choose one of these reference frames I was introducing on the slide before, we can, in this sense, complete the quantization program and write down the dynamics with respect to these physical Hamiltonians. Now, this was for closed systems. How can we transfer this to open quantum systems? And I'm especially interested in open quantum systems that involve gravity. So if we think about open systems, we usually have a system of interest, that could be some matter field, and some environment, which in the case that I would like to focus on will be gravity, because we are interested in gravitationally induced decoherence. Also in open quantum systems, we usually start with a Hamiltonian, a total Hamiltonian of both parts, which includes the free evolution of the system, free evolution of the environment, and some interaction. And in simple open quantum models, we assume the interaction is just given by some tensor product of system operators S alpha and environmental operators S alpha. The total dynamics is described in terms of density matrices, so in terms of the von Neumann equation. And in order to get an open quantum system, we trace out the environmental degrees of freedom. And what we obtain is an effective dynamics for the system density matrix here, which includes the free evolution of the system, and then some additional contributions which come from tracing out the environmental degrees of freedom and which describe the effective influence of the environment onto the system. One part is in addition to the unitary evolution, which is also sometimes called the Lemshift Hamiltonian. And there's a second part, the dissipator, which includes things like dissipation and decoherence. Now, if we choose gravity as an environment, we would be able to formulate models for gravitational induced decoherence because this dissipator comes from tracing out the gravitational degrees of freedom. We were interested in this because we wanted to look how neutrino oscillations are modified if we take the neutrino as an open system where we couple it to some environment, in particular a gravitational environment. So how do we do that? So the idea is to use a linearized gravity as an open QFT model. So this idea is not new. There is already a lot of work in the literature, also especially by Charis here, who worked with his collaborators on exactly linearizing gravity and coupling some matter field, either a scalar field or a photon. And what we basically added to the existing work in the literature was that we use Ashteca-Barbero variables and that we emphasize this relational perspective in formulating the models. So linearized gravity is good for two reasons. First, you weakly couple to the environment, so gravity should not be strong. Secondly, if we look at the Hamiltonian of GR, it wouldn't be in that form, that you have a free evolution of the system, free evolution of the environment, and some interaction. But if you do perturbation theory, then this situation is given. So what do? We basically consider the Einstein-Hilbert action and couple some scalar field or photon, and then linearize or perturb the geometric sector, which in our setup is perturbing the Ashteca variables. And then we can write down the second order action in these perturbations, which gives us directly the interaction part from the field theory perspective, which in quantum mechanical models for open systems you usually postulate. Here it's just the energy momentum tensor on the background metric of either the photon or the scalar field coupled to the perturbed metric, H, which is a function of the perturbed densitized triads in our case. Now we are in the same situation. It's still a constrained system, even if it's linearized. So we need to perform the 3 steps to get a true Hamiltonian system, perform a reduced quantization. And here we do not choose meta clocks as in the case of full LQG or meta reference frames, but we choose so-called geometrical clocks. But in a similar manner, we want reference frames at the classical level that are canonical conjugate to the linearized constraints, up to the order and perturbation theory that we are interested in. So kappa is our perturbation parameter around the Minkowski background. And then we can write down these reference frames in the linearized phase space. We call it geometrical clocks because for the Hamiltonian and diffeomorphism constraint, these are combinations of the linearized geometric perturbations. And then we have an additional clock for the SU2 Gauss constraint here, which is also constructed completely in terms of geometric degrees of freedom. So these G deltas here are the Green's function with respect to the Laplacian of the spatial part of the Minkowski metric. If we couple a photon, we get an additional U1 Gauss constraint. So we get this additional photon clock here. And then this is a set of a reference frame for linearized gravity. And we can use that to construct the corresponding gauge invariant quantities for the remaining metric degrees of freedom and the remaining photon and scalar field degrees of freedom. So we apply the same procedure, but just in a perturbative manner. We apply our observable map. And we also had to introduce a kind of dual map in which we switch the role of the constraints and the clock in order to get the final observables. And then we can determine the corresponding physical Hamiltonian. And here we were interested in finding these kind of set of reference fields or reference frames such that once we apply these 2 maps, we get the usual symmetric transverse traceless degrees of freedom for the geometry. Now we played a little bit with choosing different set of observables, and as expected, the physical Hamiltonian changes. And we could see either, should not be the self-energy, but the self-interaction that enters in this physical Hamiltonian in the case of linearized gravity, basically is there in the physical Hamiltonian or is not there, depending on the choice of set of observables I take. If the physical Hamiltonian simplifies and the self-interaction is not there, it carries over to the fact that the observable algebra is more complicated. So here we also see, depending on the final set of observables you choose, either your quantization is more complicated or your physical Hamiltonian. And since making the algebra is more complicated is always more challenging for quantization, we choose the version where we have the self-interaction in the physical Hamiltonian and the algebra as simple as possible. Given that, we can now quantize this. We use the Fogg quantization in second order time convolutionless truncation in terms of an open quantum system. And then we could derive the field theoretical master equation, which has a similar form as I was showing in the simple open quantum system model. We have a system Hamiltonian, which is either the Hamiltonian of the scalar field or the photon. U is this self-interaction term, which comes into the dynamics because we couple the photon and the scalar field to linearized gravity. And then we have this additional contribution coming from coupling to the environment and tracing out the gravitational degrees of freedom, the Lamb-shift Hamiltonian, and the dissipator. Now, the dissipator is of course different if we couple photons or scalar fields due to the fact that the system operators that enter here see whether it's a photon or whether it's a scalar field that you couple to linearized gravity. Now, if you look at these expression here in the dissipator, it has already a similar structure as the Lindblad equation in terms of how these system operators enter in the dissipator. But there's a big difference because these prefactors R, A, B here still depend on time. Yeah? And for a standard Lindblad equation, we would require that these coefficients here are time independent. Nevertheless, even if we use a different set of variables, Ashtekar instead of ADM, we could confirm the results that were already in the literature where people used ADM variables. And since we reduced to the physical sector, this is also not too surprising. Nevertheless, this is a master equation with respect to the specific frame I chose, which means if I would change that choice, the specific form of these Hamiltonian and the contributions here will change in general. Okay, how much time do I have left? 2 minutes. Okay, then I maybe just briefly discuss. Given these field theoretical master equations, they are usually very complicated. So in order to get some intuition, what people do is they, for instance, project to the one particle sector. Or they apply Markov approximations, rotating wave approximations, to get some idea what the physical implication of these master equations are. So what we were interested in is to project to the one particle sector and then consider the renormalization of this master equation, because in general, these master equation at the field theory level include still UV divergent terms. So if we do that, we can write down the projection to the one particle sector, just projecting the density matrix to that sector, and then inserting this into the master equation, we get still a complicated master equation, but better to handle than the full field theoretical case. And the state that we choose for the environment was a thermal state, which means these coefficients here in the one particle master equation include some vacuum contribution encoded in these one factors here and some thermal contributions included in these n of k. Now the idea was to identify the UV divergent terms already at this level before any further approximations are applied. And the strategy to identify them was to use some techniques that were already in the literature by these people, where they identified contributions in the master equation to corresponding Feynman diagrams. And in their model, they were using a scalar field coupled to a second scalar field, so we had to slightly generalize this to the case of a gravitational environment. And if we do that, we can introduce corresponding Feynman diagrams for this one particle sector. We have a scalar field propagator and a propagator for the gravitational part. We have the simple vertex, and we also introduced a second order vertex, which we couldn't split into first order vertices, but which we could use to identify certain parts in the master equation. Then we were looking what are the UV divergent terms, and we could show that basically this diagram of the vacuum self-energy is the one that is causing the UV divergent terms. Most terms which include thermal contribution are finite. And then we could use standard renormalization techniques in order to get rid of these UV divergent terms and get a renormalized one-particle master equation. Then we were considering under which conditions we can apply a Markov and rotating wave approximation. And since we wanted to go to neutrinos, we were mainly interested in the ultra-relativistic limit. And if we do that, we end up with this model here, which indeed has a Lindblad-like form, where the system operators are just the Hamiltonian of the system that you couple to gravity. And the evolution, the unitary evolution, is then also given by the corresponding system Hamiltonian. This was a model which was already in the literature, suggested by Bankova and Hume in 19, and which we also used in the analysis of the modification of neutrino oscillation due to the coherence effect. So let me finally summarize. Do I have 1 more minute? Okay. So I hope I gave you an idea in this talk that the classical theory, if we want to formulate it in a relational manner, prefers certain choices, I would say, of reference frames if your aim is to complete the quantization program. At the classical level, of course, you have this huge freedom to choose any, and the main restriction that come if I go towards the quantum theory is whether I'm able to quantize the observable algebra or not. So the idea is to choose these dynamical reference frames which are part of the system, which are also moving in space-time, so it's not an external non-dynamical observer. For closed QFTs, we were able to apply this to general relativity and get this perspectival approach to loop quantum gravity using some specific choice of dynamical reference frames. For open QFTs, we considered a photon or a scalar field coupled to linearized gravity. And there we followed the same idea. There we used reference fields completely constructed from the geometrical degrees of freedom, usually called geometrical clocks in our community. And if we couple a photon, we also dealt with the additional U1 gauge constraint by introducing additional clock made from photon degrees of freedom. Then I discussed the master equation and its renormalization. So what is an outlook? Basically, we can generalize any choices we made in the steps 1 to 3. So for instance, for the open quantum system, would be interesting to consider fermions in the field theory setting. Also, everything I discussed here chooses reference frames at the classical level. So an interesting question is how much of this we can generalize to the quantum setup. Since we are in a field theory, this is more complicated than in simpler quantum reference models. And also the question which was recently raised in a paper by Thiemann is, should a quantum reference frame be gauge invariant? So should I construct it at the physical Hilbert space? Maybe something we can talk about in the discussion. And moreover, the third step where, for instance, here in the open quantum model, I still chose a Fock quantization, it would be interesting to generalize it in the direction that we also quantize open quantum systems using an LQG-inspired quantization and see what are the differences to open quantum systems where I choose a Fock quantization. And with this, I like to finish and thank you for your attention.
Thank you very much for this super interesting talk. So, time for one quick question. Lin Qing?
Okay. Then I'll ask about the second part of your talk when you have linearized gravity coupled with matter. Would you have some observable that from the matter sector that could tell apart, for instance, the this observable encode the canonical commutator from the gravitational field, and therefore one can use this observable to tell apart the quantumness of the gravity versus whether gravity is semi-classical quantum. And it seems like those results would already encoded in your calculation, and one probably can read it out.
Yeah, so Again, I should say observable, like in Kasha's talk, is in a sense a theoretical observable, just being gauge invariant. It doesn't mean necessarily that we can measure that. So in these open quantum systems, before we quantize, we are already at the level where everything is gauge invariant. So in principle, everything which is in the equations should be observable in the sense that at least it satisfies gauge invariance. But if you think about a specific experiment, you would say, for instance, go to these neutrino oscillations, consider how decoherence is modifying neutrino oscillations. Yeah? So then you use the evolution of the density matrix, and you can do that in a closed system and compare to what happens if the system is open, and then, for instance, compare the two cases and say, okay, the dissipator is influencing neutrino oscillations in this way. And that would be a meta observable, which is defined with respect to the frame I choose. The frame is designed in a way that the physical degrees of freedom in the gravitational sector are exactly the two symmetric transverse traceless degrees of freedom. So if you would switch the frame, you might change this. And then, of course, the physical Hamiltonian changes, which means also the parts in your in your master equation would change in general. So does this answer your question?
We can discuss further later. Thank you.
Okay.
Okay, in the interest of time, let's thank Kristina again. Thank you.
Thank you.